Hello. This paper is from a journal called Interfaces, which is one of my favorite journals because it actually is required that any academic who does a project with a company actually gets a letter from the company explaining how the model or the tool was used and deployed at the company and the kind of benefits that it produced. So Interfaces is an excellent journal that actually takes a lot of the technical details and sort of rises them up to more of a what the model's really doing rather than the X sub ijk's. But it's always a partnership between academia or consultants and an industry partner who actually uses the IE tools and techniques. So this paper from Interfaces is about supply chain optimization and planning at a cement company in Greece. This company was founded in 1911, part of Lafarge Group. Lots of information here. They make a variety of different products. But the idea is that they have 3 plants, and there's a map coming up sort of showing you the topography of where they're located, or the geography. But they produce 9.6 million tons annually, that's their capacity, and they have 10 different quarries where they get their raw material for making the cement. A lot of different materials go into making it. And we have distribution centers as well as tanker trucks that actually deliver the materials to the different facilities. So hopefully you're already starting to get a feel for how the supply chain is set up with different locations, different transportation links or edges, and different nodes, which are the DCs and the production facilities. Now, if you look at Greece, there's a variety of different plants, DCs, and quarries. You might understand that there's ocean between all of these islands. So some of these aspects are actually dealing with sea transport besides just on the road driving. So this has what we'll call multimodal logistics inside of it because there's multiple modes of transportation at play. If we think about this type of company and the products they deliver, they sort of have 2 different ways they handle product deliveries to their customers. This CIF will be repeated in different parts of the presentation. It stands for cost, insurance, and freight. In the CIF mode, the delivery is to customer locations, either using Heracles' own fleet of trucks, that 330 that I mentioned, or third-party logistics firms or contracted trucks. When we price it out, we do price transportation costs into the product's cost for total costs. And we have to deal with when they want the product based on their location, directly leads to us talking about the available lead time, where I'm headed, what kind of fleet I already have committed to other parts of my supply chain. So there's many different aspects if they wish to go CIF, sort of like, I would say it's almost like turnkey. I place the order and it shows up. I'll pay a premium for that, but I have a quoted lead time and they'll deliver within that window to keep my customer service expectations met. The other option is called FOB, or free on board. That idea is sort of like a pickup. So sometimes you go out to eat and sit at the restaurant, and sometimes you don't want to wait and you pick up the food and you take it with you. Well, this is the idea of if you have your own transportation or you can secure your own transport, you can actually show up at the site and pick up your order yourself. So there is no transportation cost I have to pay, and the lead time is much shorter. It could be that I place the call in the morning and they say, yes, it's ready for you at 2 p.m. It could be that it's ready for you tomorrow. So 2 different modes if I want to handle my own transportation or if I have my own fleet versus more of a turnkey or full service. The company, prior to looking at an optimization approach, was using spreadsheets. As I mentioned in the last lecture, the world does run on Excel, using spreadsheets for production planning, for MRP, distribution, everything you need to run the supply chain with, they were doing on a spreadsheet. So when they look at this idea, they developed a tool called the SCOP, the Supply Chain Optimization and Planner. I think I've seen this name on many different companies' tools. Pretty clever, but everybody needs an acronym, I guess. The idea is that we're trying to synchronize our production plans, our inventory control, and our transportation, the things in the supply chain that matter, that actually can cost us money or save us money. So rather than sort of living in our own little world and doing production planning separate and then having somebody else deal with inventory and potentially somebody else dealing with transportation, I want to try to make it more of a monolithic or single piece or one decision at a time sort of a methodology. I want to make sure that planning and budgeting is in line when I'm looking at the whole supply chain's operations. I can plan, but I also need to know what budgets I have available, what resources, what capacities I have available. And because I can build this optimization model across the entire company, Even though it's only on one country of Greece, it's still a step in the right direction when we're trying to do, when we say global optimization, we're not talking about the geographic sense of global, but the idea is over the whole supply chain, analyzing all of its operations so that I can reduce costs and be more effective at making profits. So this SCOP system does a variety of different things. There's different aspects of it. So fleet sizing and planning worries about, I have so many trucks with certain capacities. Do I need more? Where do I put them? Where do I base them? Where do the drivers potentially base the trucks out of for my daily transports? I look at optimizing the use of my capacity across the multiple plants, the different distribution centers, making sure I'm making the right products at the right place at the right time. And that should become very familiar to you, hearing me say that. As well as optimizing the network in terms of allocation, much like the Continental Tire study, trying to figure out where I put things, where I ship things, where I manufacture things. In addition, we're looking at raw materials as part of the equation. Because when I get the aggregate or the rock or the sand or the different parts that go into cement, I have 10 different quarries. The ideas of where I get it from, how I ship it, what the capacity at the quarry is, how I ship it, where I make the final product, all of these things come into play when I'm worried about making a final product that has a variety of raw materials that can come from different sources or different locations. And the idea, again, is connecting into this ERP system, this Enterprise Resource Planning System. People like to use SAP and Oracle, and there's many other ERPs. But the idea is that I want to coordinate raw material purchasing with inventory levels, with transportation, with production. Now, in my experience, these ERP systems are useful. People buy them out of the box, and then they pay a lot of money for consultants to come in and help implement certain modules or certain aspects of the ERP that the company wishes to turn on. I would say every company does it the same, and every company does it different. Not everybody deploys all modules. Not everybody gets as much as they can out of every module. But it's always interesting when we have things like inventory policies or my order entry system or capacity planning. Different modules that companies have on or off directly indicates what they're really using their ERP for. Given the fact that it's a centralized data repository, there could be a lot of good data in there, but what we really want is good information in there. In this age of big data, there's lots of data. My cell phone has plenty of data on it. Whether or not it's valid information and what we make of the data is sort of the key. So they have a nice diagram as well, and you mentioned here before, like I mentioned in the previous lecture, where we have different time frames here. So they have long, medium, and short term. Again, strategic, tactical, and operational to me. And you see they have the operational model, and their demand forecast feeds the network optimization model, which they actually work with what they say is no constraints. So in other words, they want to say if we had no issues in our supply chain, what is the best way to do it, regardless of any capacities or limitations that I might have in reality. And I get what I would call that unconstrained optimal solution. That might suggest some sort of network equilibrium, meaning, well, I'd really like to send more business to the northern part of the country. Or I really need more trucks in this western part of the country because that's where it seems a lot of the demand is being sourced out of. So by unconstraining it, we basically are just saying, here's my objective function, minimize it or maximize it. And let's see what the decision variables become. And then let's start layering constraints on it to see what I can do in reality versus what the ideal case is. As I come down further and I look at what's called the tactical fleet sizing module, it says it's a mixed integer module. That just means some of the decision variables are continuous, meaning they can take on any rational values, positive or negative. Most likely these are non-negative variables. But then they have integer variables, which makes it harder to solve when you might want to say, I need 4 trucks. You can't have 4.1 trucks. The tendency sometime in practice is to solve it as a linear program, get your fractions, and just round everything up. But you can demonstrate pretty quickly that by doing that, you could actually be hurting yourself in some dimensions rather than solving it with the integer variables turned on. As we look at their planning cycle and the operations modules, they have inputs down here at the bottom from their ERP system, from their voyage calculations based on the C requirements. And all of the outputs are listed over here on the right. The network topology is sort of the configuration of the network. Where are the nodes, where are the arcs, who ships what to where when. I have different rules for the fleet size and the mix of kinds of trucks. I have the idea of where I'm going to ship things, all the way down to the production and the logistics plan, getting to where am I sourcing, which DCs, which regions are shipping to where. So they have a variety of levels of decision making in this paper, looking at what types of questions are being asked. I thought it was particularly of note to point out to you this no constraint approach. Often people will run an unconstrained optimization just to see what's possible. Then they will run and see, with their actual constraints, what's practical, and see what that gap is between them. That might help motivate future investment directions or decisions. So this operations module is set to minimize cost. As I mentioned before, we can also set up models to maximize profit. Then you would just have to bring in the sales price or the revenue side of the equation. But the different kinds of costs they're dealing with here are both the bulk materials and bagging. So whether we make bulk cement or bagged cement, we have the ability to produce them in certain ways, and there's different costs associated with them. Obviously, in the bagged case, we're dealing with extra materials in terms of the bags, maybe the machines or the personnel required to put them in the bags. Hauling, transportation, delivery. I've got the ideas of raw material costs. And then the different inputs that feed it are things like a demand forecast. And as we mentioned before, if the demand forecast is good, this can be a very fruitful exercise. If the demand is highly variable or stochastic, we might want to look at alternative scenarios, different what-if cases to figure out what is the different decisions I'd make as the demand moves to different extremes in terms of, well, this is the most I could ever sell, or this is the least I would ever sell. In that way, we can sort of paint a picture of the solution landscape, if you will, rather than a single answer. Different planning horizons, whether I want to run the model for a 6-month look or a 2-year look, I might get different decisions, different production locations, and all of these are driven towards making sure I can get the stuff to the customer in an acceptable amount of time. So this idea of enhancing customer service levels is about making sure I can deliver on time with as small of a lead time as possible to keep my customers happy. And if I miss a delivery, there could be a penalty that's monetary. There also could be a penalty that is even worse than that in terms of I lose the customer forever. So we talk a lot in the EPC world about liquidated damages and missing due dates and drayage costs for transportation providers. There's always a trade-off between the time you need to do it, how much it's going to cost you, or what they're going to pay you. And finding out that sweet spot and what you can live with and what you can deal with is part of what this optimization modeling is going to do for us. If I think about the outputs of this SCOP model, it is pretty standard in terms of a supply chain optimization model. I understand production levels, production plans, where I'm going to put my transportation assets, where I need to haul what materials from where to where, and the logistics span is sort of the coordination of all of it across all modes of transportation, across the raw materials and the production facilities and the supply chain. The idea of telling me which customer region, so rather than model it at a specific customer level, they might look at a region. So I did a project for Walmart, as you've seen in previous lectures, where we looked at 3-digit zip code regions, because that is a way to sort of collect anybody who's shipping out of that area. It's small enough of a region that I can handle it in the optimization model, but it's big enough to capture the different types of customers. So here they're using customer regions as well to figure out production plants, excuse me, production plants and DCs, and how I assign them to who gets their products from where, who gets their products made where. We also figure out which plants ship to which DCs, as well as how much I'm going to make at each plant, and the different transportation quantities. So this is sort of the whole supply chain network. You can think about the production facilities, then you can think about the DCs, then you can think about the customer regions. And you can hopefully picture the nodes and arcs and how those things are connected together. The optimization model, if you will, is giving you a picture of which arcs are turned on, which arcs are connecting which nodes to show us the whole supply chain. And from this, we can go down to a lower level, looking at actions for scheduling, production planning, as I mentioned before, maintenance, procurement of raw materials. So once I have this sort of top-down plan from a strategic view, and I take it down to tactical, then more towards operational, I can start informing my entire supply chain and coordinating decisions across different locations, such that if one facility goes down for an annual maintenance, I want to make sure that I don't take all of my facilities down at the same time for maintenance. I can coordinate or plan those across the supply chain. We also have to deal with, as I mentioned, the islands around Greece. We have to deal with the need for ships. And as I figure out my global supply chain optimal solution, if you will, I have these trucks, but I have to have some potential reality that I need ships to haul goods from the southern part to the northern part or across a body of water. So involving this multiple modes of transportation is another aspect of this model that I like, because it's not always just as simple as this is a 53-foot trailer and this is how much weight it can haul. Because I would imagine hauling cement, you're going to weight the truck out before you cube it out, and if the truck can haul 40 or 45,000 pounds, the amount of cement required to do that would quickly weight the truck out before it cubes it out. Well, in terms of the ship, ships have certain capacities, certain costs, certain availabilities in terms of their sailing dates, certain lead times in terms of how long it takes a boat to move, when you have to have your material there so they can get it loaded on the ship, dealing with different questions like what else is on that ship besides my own goods, or do I have enough volume that I'm going to commandeer the entire boat for my own product. So there's many different ideas in terms of the sizing of the ships I need and the quantities of ships that I need so that I can meet these customer demands on time. So part of the paper is telling you why it was so good. And like I mentioned, in this journal, it's about companies saying why it was so good. So they do have a centralized production planning functionality now. They have coordinated decisions across different functions of the business, so different, inventory, warehousing, transportation, all of them are singing from the same sheet of music here. And by building this optimization model, we can find synergies or opportunities to integrate decisions with tactical decision making, to integrate production planning with transportation, such that I can look for cost savings that I didn't know were there had I done each thing in isolation as they had previously done. We talked about demand volatility, a lot of uncertainty analysis here. Well, they could use Monte Carlo simulation. They could do what-if analysis using the optimization model. As you recall, Monte Carlo simulation, we can have actually probabilistic inputs, and we can run thousands of scenarios very quickly. In an optimization framework, especially with the integer variables that they were discussing, we might often come up with different sets of input data and analyze different input cases or scenarios and look at how the optimization model performs. So maybe you run 5 to 10 to 15 scenarios in an optimization framework, whereas in Monte Carlo, we can actually put the distributional assumptions around the data, whether it's triangular, normal, etc., and we can run hundreds of thousands of simulations in a matter of minutes. And we talked here before is that they were able to stratify their decision-making timeline into short, medium, and long terms. Again, from top to bottom here, operational, tactical, and then strategic. So being able to granulate or make sure their decisions are made over an appropriate time period was an added benefit coming out of this tool, because we don't want to make decisions on a weekly basis where I'm going to produce what products. We can't physically move things that quickly. People who run those facilities would feel like they were getting jerked around. Sometimes in the literature that's called nervousness or operator nervousness. We want to keep things fairly stable, and when we make a decision, there might be some assets or resources tied to it in terms of the equipment or the trucks we're going to keep there. The strategic level is more appropriate for making those kind of allocation decisions, because they're going to stick for a year or two or more until we decide to reanalyze our network, maybe because we acquired a new company or we have new infusions of capital where we can buy new resources or capacity in various locations. So when they look at this SCOP tool, they looked at things like their fleet efficiency. So the outputs, some of their KPIs or their key performance indicators, looking at how big is the truck fleet and how full are the trucks. You could have 100 trucks, but if they're each 10% loaded, you have a lot of excess capacity. The optimization model can help to figure out what's the way to consolidate it. You can run cases and say, all right, I have 100 trucks and I get this cost. What if I had 95 trucks? How much customers do I upset? What is my transportation cost increase going to be, etc.? As well as the fleet chartering costs for the different sailings of the boats, as well as the sizing of the boats. And they also looked at that CIF sales in terms of that when you have your own, sort of the turnkey I mentioned. So I just place the order, and then I expect this company, Heracles, to deliver it to me. So they were looking at percentage of the CIF sales that they were able to handle on the sea to a DC and then deliver to the customer by truck prior to delivery. Part of the idea here is they wanted to make sure they really use the ships. My screen's fluctuating, sorry about that. They really want to make sure that they use the boats most effectively. So when it says saturating specific ships on specific routes, to me, that means we're trying to make sure that if I charter a boat, I want to load it up as full as possible and make the most possible use out of the quantities that I'm shipping so that it's cost effective to me. I want to make sure I'm using the right ship to the right location rather than ship everything from everywhere to everywhere. So this is more of an effective logistics coordination decision that they're making here. And make sure that when I have this plan, I maybe could get economies of scale with the shipping firms and say, look, I'm going to charter a boat from you every month for the next 2 years, and I'm going to guarantee you this much of your capacity is going to be taken. Can you give me a break on the rate? So the idea of providing a steady ship chartering requirement is sort of having a stable plan or a more effectively communicated plan for the kinds of boats I'm going to need, and the optimization model can drive us towards more effective shipping decisions in all modes of transportation, whether it be ship or truck. The idea here, too, is that when I have this uncertainty management, if I have different scenarios, different forecasts, different demand volatility, I can plan for something, but then the real world happens. Now, we always say, well, at least Mason always says, you never want to build the church for Easter. The key is you don't take your worst day or your most attended or your busiest day and size it for that, but we know that demand fluctuates over time. So if we have a certain policy or a certain plan for where we're going to make things in certain capacities, when demand escalates, we can run what-if cases to figure out if demand surges, how will we react? Where should we be able to make the products? Where do I have excess capacity? Where am I fully saturated and there is no more capacity, such that I would be in trouble if demand for a certain product goes above a certain level? In this case, we could be talking about what if the demand for bulk goes up, but the demand for bagged concrete or cement goes down? There's lots of different trade-offs and what-ifs that they can play using this SCOP tool, looking at multiple scenarios, looking at the combinations of forecast versus capacity versus the demand signal that they're seeing. So all of these aspects, having this centralized planning system based on a common data repository, helps them have more what-if capability in a more robust manner. So the organizational benefits, this is the last slide here. The idea that we're integrating decision-making across the entire organization, whether it's as big as Continental Tires or as small as Heracles Cement just in Greece, the idea is that it's integrated decision-making leads to lower cost and more effective decision-making. The idea that we know how to plan, but then with some what-if scenarios, what if something else happens? What if demand goes up? What if a facility has to shut down? We can do replanning using the same tool. Maybe instead of saying that I have 10 quarries, I can say, all right, let's assume this one quarry is down for 3 months. What would happen in the supply chain? How would we react? These types of opportunities are able to be studied in such a model. And the interesting thing here is that I like the tie-in to the fact that the standardized models are actually used by both senior management and tactical planners. Now, I would argue I don't know how big this company is in terms of what the sophistication level of a senior management is. They might run with a graphical user interface and just play what-if games, whereas a tactical planner might be doing more detailed analysis at a lower level. But the key is this enhanced communication between departments, everybody singing off the same sheet of music, like I've said probably 5 times, is all about effective communication and information sharing so that globally the company makes better, more cost-effective decisions that can lead them to increased profits. The idea that companies run on spreadsheets can also be said that companies often have rules of thumb or just sort of this is the way we've always done it, so this is how we're going to do it. And some of those can be very effective. Often as a consultant when I go to a company, I will talk to operators and people who do it for a living to sort of understand how is it currently being done, try to model that such that when I model the, rather than the as is, but the could be case, I can show a potential delta improvement. The idea is that that's a lot of what your capstone class is going to be. Part of the project is often defining the as-is situation, whether it's a process map, a value stream, whether you're doing swim lanes, or whether you're building an optimization or simulation model. We have to know what the current process does before we can figure out how to improve it and then measure the difference that we're able to make. And the idea that these rules of thumb, these empirical rules, our experience-based approach is being replaced with models that can make more effective decisions can help with more quantitative-based decisions, and as I mentioned, hopefully lead to increased profits. That's all for this lecture. Hope you have a great day.